I am 100% aware that all of you are supposed to know how to combine resistors that are connected in series and how to combine resistors that are connected in parallel. So all we're really going to be doing today is just making sure we understand why we're allowed to do those things. Okay. So I want to talk very briefly about the concept of electrical equivalence. So let's say that I have some sort of excitation source. So it doesn't particularly matter if this is a current source or a voltage source, which is why I'm leaving the middle of that circle blank, okay? And I am electrically exciting some network, okay? And these are the terminals of let's just call this network number one. And then we have that exact same source exciting some second network, which I will be unimaginatively calling network number two. So let's say that when I excite network number one, I am able to measure some voltage V1 across the terminals of network number one using a multimeter or some other form of voltage measurement tool. And additionally, I'm able to measure some current I1 flowing into the network such that we know that the voltage drop for network one is V1, the current flowing through network one is I1, and the power absorbed by network one is just the product of V1 and I1. And similarly, when I'm looking at network two, I might measure a voltage drop across its terminals V2 and a current flowing into its terminals I2 such that the voltage drop across this network is V2, the current flowing through this network is I2, and the power absorbed by this network is V2 times I2. If the voltage drop across my networks one and network two are the same, and the current flowing into network one and network two is the same, and in this case has to be true if the other two are true, the power absorbed by network one and network two are the same, then we call those two networks electrically equivalent, regardless of what is actually inside the network. Doesn't remotely matter, but if they absorb the same power, have the same voltage drop across them with a similar excitation, and have the same current flowing through them with a similar excitation, they are electrically equivalent networks, which means from a circuit analysis perspective, you could replace network one with network two and have no loss of information whatsoever. Similarly, you could replace network two with network one and you would have no loss of information whatsoever. So those are the rules for forming an electrically equivalent network. And so now we're going to take that and apply it specifically to networks that contain resistors connected in series and resistors connected in parallel. Just as a heads up, we're going to use this concept of electrical equivalence to do some pretty neat things just in a few days in this class, where we're going to learn how to do source combinations and source transformations and all kinds of other tools involved in simplifying circuits, making them easier to analyze. That's all based on this pretty simple concept of if what I measure across the terminals is the same, then as far as the source is concerned, they're the same damn thing. All right, so let's look at resistors in series. So let's say that I have a circuit which contains several resistors that are electrically connected in series. So these ellipses here just mean that this is part of some larger circuit. Okay. So I'll have some resistor R1, some resistor R2, like so, and I'm going to go out to some nth resistor so that what we are about to explain here will work for literally any number of resistors connected in series. So this is going to be my resistor R sub n. So we're going to make a couple of assumptions here. Our first assumption is going to be that our circuit is energized such that there is some current I flowing through all of these resistors that are connected in series. And there will be a voltage drop across all of those resistors connected in series. Okay. So if we define the voltage drop across each resistor, so I could call this voltage V1, positive polarity on the left, V2, positive polarity on the left, V sub n, positive polarity on top, like so. And just as a heads up, the only reason I chose the positive polarity where I chose it is so that the current would be flowing into the positive polarity terminal, so that when we use Ohm's law in a moment, everything's going to have a positive sign, because I'm lazy and I don't want to make any mistakes. So if we apply Kirchhoff's voltage law to this particular system, what we would find is that our voltage V, which is the drop across all of the resistors connected in series, is just going to be the sum of V1 plus V2 all the way out to that voltage V sub n. We all okay with that? Nothing particularly wild or crazy there, right? So what we can do now is we can use Ohm's law to express all of those resistor voltage drops in terms of that common current I. So that's going to look like R1 times I plus R2 times I all the way out to R sub n times I. And we can see very easily that there is a common factor of I. So we could write this as R1 plus R2 all the way out to R sub n times I. Well, when we discussed Ohm's law Wednesday, we learned that resistance seen between a pair of terminals, so this will be an equivalent resistance of this whole network, is simply the ratio of the voltage drop across the terminals of the network divided by the current flowing into the network. So that's just going to be V divided by I. And if we take our expression for V and divide through by I, we're left with R1 plus R2 all the way out to R sub n. And in a more compact form, using summation notation, this would look like the sum from I is equal to 1 to n of R sub I, where I is just the index on all of those resistors. So we have very formally proved what you all already knew. When we have resistors in series, we just add them together. That's the reason why. It's effectively Kirchhoff's voltage law. Okay. All right, so now let's look at resistors connected in parallel. Let me do it on another page just to give myself enough room. So we're going to have a similar situation here. I'm going to have a network that is part of some larger circuit. And now I'm going to have several resistors connected in parallel. So here we have some resistor R1. Here's some resistor R2. And then here is some resistor R sub n. So that what we are about to derive is appropriate for literally any number of resistors connected in parallel. Once again, since our circuit is, since our network is part of some larger circuit, we're going to make a couple of assumptions. There will be some current flowing into our network containing our parallel resistances, and there will be some voltage drop across our network containing these parallel resistances. So what I'm going to do now is I'm going to define my resistor currents, and I'm going to have them all pointed down. So we'll have an I1 here, an I2 here, and an IN here. And the reason why I chose that direction as down is so that the current is flowing into the positive polarity terminal, so that Ohm's law always gets a plus sign, because once again, I am lazy and I don't want negative signs if I can. So if we apply Kirchhoff's current law to this particular network, what we'll find is that I, the total current flowing into the network, is simply the sum of all of those resistor currents. So I1 plus I2 all the way out to I sub n. Using Ohm's law, we can express all of those resistor currents in terms of that common voltage V. So that's going to look like V divided by R1 plus V divided by R2 all the way out to V divided by R sub n. And we now have a common factor of V in all of our numerators that we can pull out. So that's going to look like V multiplied by 1 over R1 plus 1 over R2 plus all the way out to 1 over R sub n. Once again, the equivalent resistance of our network is nothing more than the voltage drop across the terminals of our network divided by the total current flowing into our network. And we can see that that's going to come out to 1 divided by the sum of the reciprocals of our resistances. So 1 over R1 plus 1 over R2 all the way out to 1 over R sub n, like so. And in a more short form, this is 1 over the sum from n is equal to 1, I is equal to 1 to capital N of 1 over R sub I. This expression agrees completely with what you guys learned in Engineering 120. You now know why it works. Short answer is it's Kirchhoff's current law. So all of this stuff was largely a review, or at least the results were. You might have not known the math behind it. Let's look at some interesting things that can come out of this parallel resistance relationship really quickly. Okay. So let's say that I have a network containing exactly two resistors in parallel. So let's call this one R1 and this one over here R2. According to the relationship that I just gave you guys, the equivalent resistance of this network would be 1 over R1 plus 1 over R2. While there isn't anything wrong with this relationship, it's not one that I prefer to use because it's just cumbersome. It takes a long time to put all of that into my calculator. I have fat fingers and I tend to screw it up. So instead, we're going to play around with a little bit of algebra here. Okay. So what I'm going to do is I'm going to multiply that 1 over R1 term by a very fancy form of the number 1. So I'm just going to use R2 over R2, right? That's just 1. And I can multiply anything by 1 and be perfectly okay. Similarly, I'm going to multiply that 1 over R2 term by R1 over R1. So what that does, the aggregate here, is effectively gives me a common denominator in my denominator so that I can simplify this thing a little bit. So I've got my 1 over, and now I've got 1 times R1. So I'm just going to call this R1 divided by a factor of R1 times R2. And then I've got 1 times R2. So I'm just going to add an R2 here like so. So how do I divide by a fraction? I multiply by the reciprocal. So 1 over R1 plus R2 over R1 R2 is the same thing as simply R1 times R2 over R1 plus R2. And this is a quick and dirty way of calculating the equivalent resistance when we have exactly two resistors. So this method technically only works for exactly two resistances in parallel, as it's shown. So let me explain what I mean by that. Okay? So if I had a 10 ohm resistor in parallel with an 8 ohm resistor in parallel with a 6 ohm resistor, if I do Req as 1 over 10 ohms plus 1 over 8 ohms plus 1 over 6 ohms, I will get some number that I can't figure out off the top of my head. So I'm going to use my calculator real quick. So 1/10 plus 1/8 plus 1/6. So I got 120 over 47 ohms. Or for those of you that prefer decimals, 2.553-ish ohms. Now, if I tried to do Req as R1, R2, R3 over R1 plus R2 plus R3, I will not get the right answer. Can anybody tell me why just by looking at it? Yeah. So if we look at the units of this thing here, what are the units of the numerator going to be? Ohms cubed. What are the units of the denominator going to be? Ohms. Is ohms cubed per ohm an ohm? It is not. So fundamentally, that has to be wrong. Okay. What we can do instead is the long thing that you said, which is nothing wrong with it, but I'm lazy, so I'm not going to do it. We can just lump two of these resistors together, and it literally doesn't matter which two, to find the equivalent resistance, and then use the two resistor equation to bring in the third one, and we will get the same result. So if we replace the 10 ohm resistor and the 8 ohm resistor with a single equivalent resistance, what would we get? I think it's 80 over 18 because R1 times R2 over R1 plus R2 is really easy to do. Right? So I hope we can all agree that 10 times 8 is 80 and 10 plus 8 is 18. We good there? Okay. Yes, that could be simplified. No, I'm not going to do it because, again, you do not know the bounds of my laziness. So we would take that, have it in parallel with the 6 ohm resistor, and then we would have 80 over 18 times 6 over 80 over 18 plus 6 and we once again get 120 over 47 ohms. So if I have only 2 or 3 resistors, I'm probably going to do it this way, where I'm just using the 2 resistor combination method twice to get the equivalent resistance. If I have 4 or more resistors, I'm going to do it the old way because it's just less typing and math on my behalf. So I just want you guys to be aware of this kind of shortcut. Okay, so not all of the time are we going to have the luxury of just having things connected in series or just having things connected in parallel. We're probably going to have some networks where there's going to be some ambiguity to things. We've seen that already in this class. So what I want to do real quick is I'm just going to pull up a WebWork problem and then redraw it because I didn't think to bring my other tablet to be able to do both things at once. And I'm going to show you guys how I like to combine resistors. So looking at homework set number 3, let's look at problem 2. So this is a relatively ugly-ish network. And so now I'm just going to try to effectively copy that thing down. Okay. So my memory is the hottest of garbage, so I feel like it was something like this. And let me see if I can easily switch over. Did I close that window out somehow? Apparently I did. That's annoying. So let's see, we have R2 is 100 on top, 100 on the left, 25 on the bottom. So I don't want to exit anything. Quit being a weirdo, computer. That's going to annoy me. Let's see, R4 was 52 ohms. We have 50 through that middle branch and 280. So that is 52, 50, and then 280. And then lastly, we have 82, 75, 200. And our nodes are labeled CBA and then D in the bottom middle. Okay. So C, B, A, and then D down here. All right. So what I would like us to do is take a moment and identify all of our nodes in this circuit. Okay. So we haven't done this since really the first day of class. So I'll remind you guys of how I like to do it. Effectively, I just start at one circuit element and keep going until I hit another circuit element. And I have to take care of all of the paths that branch off this node. So I've got this red node in the top left where the two 100 ohm resistors and the 52 ohm resistor are connected. We're going to call that node C because it's already got a node label on it. We've got this blue node here that'll be in the top middle. We'll have a green node over here on the top right. We'll have this light blue node here in the bottom left. Maybe an orange one for this bottom node that's connected to 5 things. And lastly, a light purple node over here on the bottom right. And because that bottom left node and that bottom right node don't have a label, I'm going to give them a label. So I'm just going to call this one E and this one F. So as part of this homework problem, you are asked to find the equivalent resistance seen between particular pairs of terminals, okay? So for part A, you're asked to find the resistance between terminals B and C. For part B, you're asked to find the resistance between terminals B and D. And in part C, you're asked to find the resistance between terminals C and D. So I want you guys to tell me whether we're answering A, B, or C. It's all going to be similar, but they are not going to be the same thing. So just A, B, or C. Somebody? C. Okay. So we're trying to find the resistance seen between terminals C and D. So RCD is equal to question mark. So I grew up watching a little show called Pee-wee's Playhouse. And on Pee-wee's Playhouse, they played a game called Connect the Dots. And so that's how I combine resistors, literally by playing Connect the Dots with resistors. So I start by putting the two terminals that I'm interested in on opposite sides of my page. So I'll put C over here on the left, and I'll put D over here on the right. And what I'm going to do is I'm just going to map the various paths to go from C to D by connecting the dots or the nodes with resistors, okay? So is there any way that I can go directly from node C to node D through a single resistor? What is it? The 52 ohm resistor, okay? So I'm just going to draw a direct path and put my 52 ohm resistor here. And I'm also going to put a little check mark by this resistor to remind me that I've already taken care of that path, so it should not show up again. Okay. Now, is there another way that I can go from node C to node D? Well, yeah, there's several different ways. So I typically choose the shortest way next, which to me looks like I would need to go down through node E and then across to node D. So I'm going to put node E here in the middle of my page, and I'm going to go from C to E through the 100 ohm resistor, which is this guy right here. And then I'm going to go from E to D through the 25 ohm resistor, which will be this guy over here. So it looks like I've got that left hand or bottom left hand corner pretty well taken care of. So now we're going to start looking at the paths towards the top and the right. Okay. So it looks to me like I can also go from C to D by going through node B. So let's put node B right here. To go from C to B requires me to go through the 100 ohm resistor on the top left, which is this guy. And then I can go from B to D directly through the 50 ohm resistor in the middle. But there are other paths that I can take to go from B to D as well, right? So I could go from B to D through node A. So we could put node A right here. So from B to A is the 82 ohm resistor. And then from A to D directly is the 280 ohm resistor. So that takes care of this guy and this guy, but I can also go from A to D by going through node F. So I'll put it down here. So from A to F is the 75 ohm resistor, and from F to D is a 200 ohm resistor. So I've taken care of all of the different resistances in my network, and now to me, this is actually something that's much easier to simplify because I can literally just work my way from the bottom towards the top. So how are the 75 and the 200 connected? Well, it looks like they're in series. That equivalent resistance is in parallel with the 280. That equivalent resistance is in series with the 82, and so on and so forth until I work my way up until I'm just going to have 3 resistors in parallel, and then I'll throw that into my 3 resistors in parallel equation. So it takes that big, ugly network and puts it in a form that can be easily simplified just by playing connect the dots. So that's how I like to do it. And even as somebody with a PhD who's been doing this for years and years and years, this is how I do it 100% of the time if I can't look at it and just know what's going on. All right. I'm done. Well, 2 minutes earlier than I thought. So you guys have an in-class assignment. By the way, for that in-class assignment, there is a big, ugly kind of network on the right-hand side. I would encourage you to find the equivalent resistance of that thing first, and then use that to make all of your other calculations easier. Then you also have a mini lab. The mini lab you can do at your tables. It's just finding the equivalent resistance of a particular network from different node points. So you don't need a power supply or anything like that. I will grab a whole bunch of jumper wires and just put them up here for you guys to use at your leisure.